Welcome everyone. In this video we're going to be talking about chemical equilibrium. So a lot of this will be kind of a review, right? But some will also be new, hopefully, right? So, right, every chemical reaction will reach a state of equilibrium. Now, some chemical reactions, the equilibrium is so far onto one side of the reaction than the other that we don't really consider it an equilibrium reaction. But every reaction technically is an equilibrium reaction. That every reaction will reach some type of equilibrium. Okay. But again, you can have reactions that so much favor the products that you never really think of it as an equilibrium reaction. Okay. And that equilibrium thermodynamically is just related to the minimum free energy along the reaction kind of diagram here, right? As the reaction is going, when the free energy of your system is minimized, right? That is when equilibrium is established. Okay, right? At equilibrium, okay, right? If we remember our definitions of chemical equilibrium, right? It's a dynamic equilibrium, right? The equilibrium does not stop. Okay, right? The reactions don't stop, right? The total concentrations remain constant at some amount, right? But the reaction itself does not stop, right? What those values, those final values are, doesn't necessarily depend on what the initial values are, right? But again, it's a dynamic equilibrium, right? The reactions are still going, both forward and reverse reaction are still occurring, right? They just occur at equal rates, and thus you establish this equilibrium between these two reactions, right? And as we remember, right, these equilibrium constants, right, concentrations of products over reactants, right, so your stoichiometric coefficients, right. In general chemistry, we'd use concentrations or partial pressures, right. Here we might do the same as well, or if you're trying to be more accurate, more careful, right, you would use activities, right, or fugacities in place of these concentrations or partial pressures. Okay. Right. Let's consider kind of the free energy change without mixing, right? If there's no mixing, right? If I had this reaction occurring where my reactants are in one vessel, once they react, the products get immediately removed into some other vessel, right? Then the reaction would follow just a straight dashed line in this plot, right? Where assuming products are lower free energy than reactants, right? All reactants would eventually form products, okay? But, right, that is considering an unmixed system, right? Where my reactants and products are in separate containers, right? They are not mixed together, right? I extract my products as they're being formed, okay? But if I allow these things to mix, then the free energy is no longer just a straight line, but follows the solid curve, right? Right, where there's some minimum that exists, okay? Right? That minimum that exists is at point E here, representing kind of the equilibrium, okay, right? And so that minimum is occurring because of this mixing, because the reactants products are mixing, right? And as you mix things together, it changes their chemical potentials, right? A lot of times due to entropy reasons, but even enthalpy, right? Even if you don't have ideal gases and things like that, right? Enthalpy can also be a factor in this, okay, in real system. But if you're considering, say, an ideal gas, ideal solution, right, then it's just purely an entropy term, right? And the fact is that because of this entropy, right, there is a free energy that's lower than that of the pure products or pure reactants, okay? Because ideally, if I have a mixture of two things, right, 50-50 mixture has the lowest entropy possible, right? The greatest entropy possible, which means the lowest free energy, right? Now, obviously, the reaction isn't just pure mixing, right? These things are reacting, reactions are occurring, so the free energy changes as you're changing your chemical compounds, right? So that minimum doesn't occur at a 50-50 mixture of reactants and products, right? It's influenced by the free energy of the reactants and of the products, right? But you do get this minimum that occurs, again, that's not at the products or the reactants along this chemical reaction, right? But somewhere in between, right, that exists because of the mixing of these two things in the same vessel, okay? So let's consider what that is and try to kind of calculate it and relate it to things we talked about. So let's just consider simple reaction A going to B, right? With stoichiometric coefficients A and B, okay? We're going to define the extent of a reaction, okay, as sort of the fraction of the reaction that's occurred, right? And when the extent of the reaction is 0, all A is present, there's no B. When the extent of the reaction is 1, no A is present, and it's just left with B, right? So 0, no reactions happen yet. 1, everything's reacted, okay? So, okay, right? So the number of moles of A is just related with the initial number of moles minus the stoichiometric coefficient of A times the extent of the reaction. The number of moles of B is just then equal to the stoichiometric coefficient of B times the extent of the reaction, right? And so I can look at the change in number of moles, right, with respect to the change in the extent of the reaction by just taking that derivative, okay, of those two equations to get that here, right, dNA and dNB, right? Okay. And so from that slide, right, let's now consider a free energy change as, right, what is the change in the free energy of this reaction as I'm increasing the extent of my reaction, right? As I'm going from 0 to 1 for my extent of the reaction, okay? So again, my free energy change for the reaction is related with the change in free energy with respect to the change in the extent of the reaction, okay? Well, again, that free energy, right, so some change in free energy is related with the chemical potential times change in the number of moles, right? I can relate the change in number of moles with the stoichiometric coefficient and the extent of the reaction, okay? Right, I have some minus sign for the reactants, positive sign for the products, right? And so my some change in free energy of my reaction is related with the change in the extent of the reaction by this term here of minus A mu A plus B mu B, right? And that is again related with the free energy change of this reaction, okay? And so the free energy change of the reaction is just minus A mu A plus B mu B, okay? Right, and these chemical potentials A and B depend on the actual composition that's occurring in the reaction, right? So they're dependent upon what is the mole fraction of A, the mole fraction of B, and things like that, right? Well, equilibrium, right, occurs when we've reached the minimum free energy for the reaction, right? Right, so the minimum free energies are going to occur when the free energy change is 0, so the change in the free energy of my reaction, it reaches 0, okay, right? Because if we think of that plot, right, the minimum occurs, right, when delta G here now equals 0, right? Because this plot is, say, G versus the extent of the reaction, okay, right? And so the minimum is when that free energy change is no longer changing, right? And that then occurs at this point here. Mu A equals B mu B, right? And so that is when equilibrium occurs, okay? So equilibrium in a reaction occurs when the sum of the chemical potentials of the reactants times their stoichiometric coefficients equals the sum of the chemical potentials of the products times their stoichiometric coefficients, okay? Where again, these chemical potentials depend on the composition, right, the mole fractions and things like that, concentrations, right, of your reactants and of your products, okay? Right. And we'll talk more about that in the next video, okay, about how these chemical, right, how the chemical potentials, right, depend on the compositions and things like that to eventually rederive kind of what we've seen for equilibrium, okay? But again, just to reiterate, right, as this reaction's occurring, right, as I'm going forward in the reaction, okay, my free energy is changing, right, delta G here is less than 0 as I'm going forward, right, for delta G for the reaction, okay. As the extent of the reaction is changing, the composition of my reactants and products is changing, right, how much reactants I have versus products, right. But once I reach equilibrium here, right, delta G of the reaction is equal to 0, and I've reached equilibrium, okay, which means I've reached my minimum, right, which means it's not going to want to go uphill, right, say, to form more products, because now if I'm going uphill, right, that delta G is going to be greater than 0 for that reaction, right, and that's not going to be favorable. That's not going to be spontaneous, right, for constant temperature pressure conditions, right, so that's not going to happen, right, so reach this equilibrium at this point, right. Now we'll talk more about this in future videos, but I want to emphasize, right, that this isn't saying that the free energy change for a reaction that we typically think of in chemistry is 0 for every reaction at equilibrium, right? Because what we talk about typically in chemistry for free energy changes of a reaction is this delta G of the reaction naught at standard temperature pressure conditions, right? Where the composition is fixed at 1 bar, 1 molar, right? So it's like 1 bar, 1 molar concentrations of your reactants and products, okay? Which is not necessarily the equilibrium composition of your reactants and products, right? Right, at equilibrium, you're not necessarily going to have 1 bar, 1 molar of everything, right? And so the free energy change, okay, of the reaction, right, is what we normally think of with the, free energy of the reactants minus the free energy of the products, right? Right, which is related to this delta G or not, right, that we've talked about actually before with chemical reactions, okay? Here, right, this delta G of the reaction, right, this is the free energy change of the reaction, right, that depends on the mole fraction of A and the mole fraction of B and so on and so forth, right? Or again, the concentration of A and the concentration of B, right? Okay.